I'm Douglas. I've been a Samba developer for about 10 years. I've been on the team for about 9 years. And I work at Catalyst IT, which is a company in New Zealand which has a sort of open source focus, but it's mostly making websites, government websites and web applications. And we do a lot of e-learning stuff. We work on Moodle, but not me. I work on Samba. And there's two of us on the Catalyst Samba team. It's me and Jennifer Sutton. And Jennifer is the clever one who does most of the work, and I do the talks. So this is something I was interested in at the end of last year when I thought I'd submit a talk. And I had a very clear vision of what I was going to talk about and what pictures I was going to have and how everything was going to work. But I thought, it's so clear, I won't forget it if I ignore it until last night. And it didn't quite work out like that, but I've tried my best. So, sorry, but you'll see. Okay, so what is an LDB index for is like the first thing. And it's to answer the question of which objects have an attribute with a certain value. So if you want to know, like a SAM account name with a certain SAM account name, the index will kind of point you straight there. Whereas if you don't have the index, you don't need to do a linear search through all the objects, which means you need to go find, you're traversing a database, you find an object, you unpack it, you search for the attribute, and then you compare the value. And there's, it's two different slides there. You can have shortcuts where if it's not in scope, you can skip that object. But you also have to do some copying, which is quite a lot of work. So it's a slow thing if you don't have an index. So what indexes do is they reduce the search space to a smaller superset of what you want. Sometimes it's the exact thing, but sometimes we use it to find a bigger group, which happens with complex expressions if you have an and or an or a mixture of those. And then because if you find a superset, it all gets pushed through to a filter that kind of goes through each one you found and makes sure that they're the right things. So if you find, if your superset has objects that don't apply, they'll just be filtered out. And how the index works is it's just a special key in the main database that has a, okay, in classic LDB you have a DN for your main object, and you have the index has a attribute and value is kind of with an index at the front becomes the DN. So it's like anything that starts with an at is a special DN to Samba. And so it can construct that special DN from your search, and then it finds it, looks for that in the database. If it's not there, then it returns no such object. If it is there, it fetches it, and I'll get to what the format is. Well, basically it's an LDB message, which is a little list or array. And then since 4.8, Samba's actually used a new mode of index called a GUID index, which is faster for all kinds of things, but the old kind is still supported because SSSD, and if there's anything else that uses LDB, might use the old way. And if your database kind of upgrades automatically when you first use a modern Samba. There were problems along the way, but I think it works now. Well, there's not many complaints. And the GUID indexing is actually quite a lot faster for some things. And then there's another complication. There's lots of complications along the way. If the attribute is not very printable, not about swear words, it's about ASCII characters and stuff. We base 64 encode it, and there's see the double colon after the attribute name. That's telling you that attribute, that value has been base 64 encoded. So you would do that maybe if the attribute was a GUID or something, I don't know, JPEG photo. So here's an example database. So I'll go through some things with this example. We've got 6 objects, ant, bee, car, dog, and egg, and we've got 2 attributes, which is legs and wheels, and I've chose these because you can probably remember that ant and bee have 6 legs, the dog has 4 legs, and a car, in this case, it's got 4 wheels, and the other one, and otherwise it's 0. So we don't need to keep going back to that. So the index for legs 6 would list bee and ant, and the index for legs 4 would be dog, and so on. And wheels 0 would have a whole lot of things, but not car. Then there'll also be entries for a whole lot of housekeeping stuff, like when changed and when the USN was changed, and other things that just kind of pop up magically. And so if you search for legs equals 6, then you construct that magic index DN, and then you read the list, which says bee and ant, and then you go through and just check that those things are right, because you always do that, which is part of the constructing the reply. Now, with an AND, there's an optimization. Oh, no, I won't talk about that yet. What you do is you look at each sub-expression in order, but it actually looks at equality. It tries to find equality sub-expressions first, which I've put in the wrong order. Okay, so it looks at each sub-expression in order, and it finds legs equals 6. It finds 2 things, and at that point it stops. It says, well, this is enough. I've narrowed it down to a superset of what it could possibly be. And then it gives that list to the next thing that is going to filter out anything that it doesn't apply to. So even though we know there's nothing that has 6 legs and 4 wheels in this database, but the index doesn't go as far as working that out. It just finds the first time it can stop, it stops. And because it finds that doesn't work, it just returns no such object, which is what that means the empty set. And that way, if you switch the arguments around, from that it does the same thing, except when it finds wheels 4, it gets 1 result, and so it makes the filtering at the end faster, because it only has to check 1 thing, and it finds it's got hasn't got 6 legs, and then it can return quicker. Now, when you're talking about the difference between 1 object and 2, it's not much, but when you get to bigger amounts, it's quite a bit, which I'll get to. later. Now, with an OR, yeah, you need the union of those two things. So this should get the car and be and at. And then so there's no shortcut with a OR. And you can't when you're finding your results, you have to actually merge them in. You can't really have duplicates in your result that you're sending to the filter, because the filter doesn't have a state that remembers that when it's going through the list, it doesn't remember that it's seen the one already. So you kind of have to do this merging, which they do by sorting each side. In classic mode, you have to sort each side before you do it, and then you merge them like the merge step in a merge sort, which just kind of means you take the lowest one from whichever list you've got until you can complete it. And now, if you've got more things. If there's an empty set, that's easy. You just skip it, and again, you find the two things in there. And an AND with lots of things, it'll just find the first one again, and it'll reduce to no clip object on the final filter, which is running the whole expression again on the objects found. Okay, so here's an optimization that AND does. Before, it doesn't actually go to the first expression, it goes to the first equality expression that it finds. So in this case, like the natural order is you kind of go down this expression forms a tree. That's how we save it. And you go down, depth first, and you'd find an empty set at the end because there's nothing with Cn equals fig. And we don't know. Now, if we did the first branch, we'd end up with quite a few things, because legs equals 0 or wheels equals 4, and then you'd filter those down. But in fact, we look for the first equality one, because then we can skip the whole OR, and it goes like this. So that whole branch is just kind of skipped. And that's the same in this case. That's an empty set that it's returning, because that's what Cn equals fig gives you. There was no fig. But if it was returning a non-empty set, it would still do this, obviously. But so it tries not to go deep in the tree. Tries to the first at the top at every level. The first equality is what the AND returns. So it returns a superset. The first simple equality is what it gives you. And if there's no simple equality, it goes down the first branch. Now, so here's in real life. If you do it, object class equals user, and Sam account name equals Bob. Now, usually there's 0 or 1 things with any Sam account name. And there are your number of users is typically how people measure the size of their domain. So it's could be hundreds of thousands. So if you do the first way, that's slow, because it just finds the first index and then it will filter through all of those and look for the Bob. If you do it the other way around, it'll find Bob or not. If there's no Bob, it will just return an empty. If it finds Bob, then it will check for Bob if Bob is the user, which is probably the case if there's a Sam account name. I don't know everything. But with OR, there's no shortcut like that. You really have to build up your set. You can't, because you're growing the set that you're getting, you can't skip early. With AND, you can. We could try things like if the OR gets to a certain point, we just give up and go to the full list or something, but we don't. So the union that is used in OR is a merge algorithm like I was talking about before. So and GUID indexes, the indexes are already sorted. And a GUID index is a list of GUIDs, which I probably should have explained. I will at some point, I think. And classic indexes, each time you're doing a union, you have to sort the list and then do the merge, and then you go on to the next one, sort both sides again, and it's actually quite slow. Well, slow enough to make people make the GUID indexes. Okay, now transactions. Transactions are a thing where you do a whole lot of operations. Either they all work or they all fail. It's atomic over a whole lot of things. The way we do transactions is we have a little TDB in front of the main one. This little one is actually an in-memory TDB, so that makes it's really just a hash table. But it kind of has to jump through a few hoops to look like a TDB, which is a little bit expensive, but we do that. And so when you come to the index, during the transaction, the index has to give the same results that the main database would give at that point in the transaction, but then if the transaction fails or is cancelled, it has to just go back to where the main database was. And if it succeeds, it has to, they both have to stay in sync. And that's the tricky part. So what we do is we have this little cache TDB in front of the main one, and we look for the thing in there, the index, and if it's not in there, we go and get the real index from the main one, and then we modify it and put it in the front cache one, and then when we're reading using the index, we have to look in the little one first. And then there's a thing we've got, sub-transactions, which we have because some operations, like a modify, a replace, and a mod RDN, which is like rename. The operation has two parts, and if you're in I think it's for LDB when we're using that back end. If one part fails, the whole thing the whole of that sub-transaction has to fail. We have to roll that back. We have to kind of roll back two things, or something, and so what we do is we have an even smaller TDB in front of the tiny one that we've got. This one has the size of the hash is, I think, 11 is what we use, because it's kind of like for one LDF stanza kind of thing, like it's saying we're changing this to yen, we're replacing this attribute with this other one, and so you need to do a delete, and then you need to do an add. And if the add fails, you need to roll back the delete. And you roll back the delete in basically by deleting the in-memory, the little sub-transaction cache, you just chuck it out, and that's gone. And then if it succeeds, you write that onto the main transaction cache. And then when the whole transaction is done, you write that main cache into the real database. And then if you need to cancel, you just sort of chuck them out. And if your transaction is an LDIF file, the sub-transaction thing makes no difference, because if anything fails, the whole thing fails, because it's kind of like there's no point you going, oh, did that sub-transaction, that sub-thing fail? Let's try something else. But in other transactions where you're actually sort of manually doing the transactions in your code, then you sometimes might want to check the sub-transactions. And if it fails, you might want to skip it. Or I don't know what you'd be doing. But it happens in provision and stuff, that we're doing stuff where there's a big transaction and we actually want to, we want some of the sub-transactions to be allowed to fail, and we have ways of recovering and then continuing. So we need this. We need to complicate everything, which we do quite well. So this is an example of a sub-transaction. It's just like an LDIF stanza. And that replace is the kind of thing that needs it. And now, what got me into talking about this and working on this is Andreas and Andreas. They both were finding bugs where LDB was really slow in big transactions, and it was to do with copying things from that little TDB into the second littlest one, and we would like tillicking and copying, doing like classic Samba, making lots of copies when we could just sort of point to the existing data. So that would be fixed in whatever number we're up to now, 422 or 421 or something. Yeah. Oh, that's interesting. Okay, so greater than and less than operations. So if you think about, yeah?
Can you go back to the slide before?
That one?
Yeah, if the attributes are like a tree of users, example, what do you do in renames of a higher node, which is like a subtree root? Like you want to change users to underscore root. This is usually the problems in databases which are not like tree structure, because if it was really tree structured, you just replaced it on like in a file system. But if it's written in the database path by path, you have to go through all the paths and change in all of them users to underscore.
Yeah. And that's the problem. That's
you don't have any like some kind of hierarchy index, like.
no, yeah. So the database, it pretends to be a tree, but it's not really. I mean, the DN, it looks like a tree, but we don't have the tree for that. But there are operations for subtree renames and stuff, but I can't remember how to.
Just not usually done, so it's not important. I don't know.
It's not often done, and it's not fast, I don't think. Like, the people around you probably know more about this.
There's databases that are tracking or like imitating a file system. It's usually a big problem. But if it would be a file path, then the directory users could have been renamed as a legitimate operation. Then you would have to go through many entries to change it.
Yeah. there is, okay, so this isn't really directly related to indexes, but there is some system for, we call it a subtree rename, which I have looked at in other years, but I can't remember how it works.
I guess it just doesn't happen a lot here. Like
Yeah.
rename or move would happen only to the leaf part of like a kind of an abstract tree. It's not a tree, but
Yeah. For people watching the recording, I'll just say that this was talking about what happens if you rename the user's, say the user's CN, and then all the other things below it need to be renamed too. And that isn't fast, and people don't do it often. Especially, actually, the users, I think, is like a special thing that you don't rename.
yeah.
The impact on indexes for that would be you just need to redo the indexes for all the ones that you changed. And there are ways we handle that where we can make it happen, but I can't remember how it works. Okay. So, with a greater than or less than operation, which is a thing you can do in the LDAP query, we only started supporting this with the GUID indexes. We use the hack, or we use the fact that everything that's in a DN that has everything in an index that has an attribute with any value is going to sort alphabetically between the DN with just ending in a colon with no value at the end, and the DN with a semicolon at the end. And so if you look, if you're doing a greater than, you're looking for everything between the value and the thing with the semicolon at the end. Because in ASCII, the colon and the semicolon are just next to each other. And because it's always going to have a colon at that point, apart from another wrinkle that I'm going to get to. So if you're looking for some attribute that is greater than or equal to true, then you just search for all the indexes in the database relationship between those two and return the union. And in this case, we can return the union we don't need to merge each one, because it's kind of like we're doing this all at once. It's an atomic kind of thing. We just chunk them together and then sort it at the end. So it's a little bit quicker. And there are edge cases. Before, I remember I was talking about the base 64 encoded things. Well, they don't really work with this greater than or less than. It's just sort of, they end up sorting, I guess they sort wherever a column would be, and then they sort however the base 64 sorts, which well, actually possibly that works if everything is base 64 in that attribute, because, or maybe not. They'll be in some order. Anyway, and then with numeric values, we have a problem with because that sorting is alphabetical, and like 123 sorts lower than 4, and negative 32. I don't know how that would sort, but not necessarily right. and then like a negative 42 would sort higher than negative 32. So we came up with this strange system of storing the numeric values in this format, where you go n for a negative number, o for 0, and p for a positive number, which, you know, the consecutive numbers, values, letters, that sort, so the n sorts below the o and the p. And then for 0 and 1, we just pad it out to as big as a 64 max could fit. And that's what we have in the index, so it's kind of readable if you're looking at your LDB indexes, which not many people ever do, but you know, yeah. But then there's the funny thing with the negative numbers. To make them sort properly, we take away, no, what do? We kind of add the minimum value so that they sort like the lowest negative number is 0 and the highest negative number, -1, is a big number. And that makes it all sort. So if you're reading it, you can read it well until you come to a negative number, and then you're baffled. There are other things we could have done, but we couldn't really work it out at the time, and this one worked. And there's another thing that's complicating. So LMDB, which is one of the backends supported by LDB, which we introduced LMDB because it could support bigger databases than 4 gigabytes, and it's not limited by 32-bit, and it actually seems to be faster. But it does some things. It's faster by being finicky about stuff, and it has a maximum key size, which you probably hardly ever hit. But if you do, you can have collisions in the key space. If, in this case, car license is like a free text field, you can put anything in there, and if you put the same text in, the text that is the same for the first 500, it doesn't need to be 511, it needs to be some number of characters to make the whole thing 511 or more long, and then you change the text after that, then you have an index that will collide. Two things will have the same index key, and that could cause trouble. Indexes wouldn't really work in that case. And so we use a different namespace by replacing the colon with a hash. And we also have the base 64 version with a double hash. And then, so if you find, so when if you find an index key with the hash there, you know that it's the long one, and that you need to look out for. You need to check whether it's a duplicate, and so that's a complication that is riddled all through the index code of trying to deal with those cases. I don't think we deal with it in every case, which I think doesn't matter in reality. But, like for example, do they work with the greater than or less than? And they clearly don't. And I think there are other situations where they don't work. It seems to me that maybe we could have done something different, like putting the SHA-256 or something instead of the value. That would actually then make it so you would actually have a unique name after your hashes. But anyway, we didn't. I don't know how much time I've got. Oh yeah? I'm going to be under time, I think. That's good. So I was working on this for a month or two last year, trying to make the transactions faster by using, instead of having that miniature TDB in front of the second one, in front of the main one, if we just have an undo log on the main transaction cache for the sub-transaction. So in the sub-transaction, you do one thing, do another thing, usually only doing two things at the most, but you just write down what you've done, and then if you, and you do that in your in-memory cache, and then if you want to undo it, if you want to cancel that sub-transaction, then you just replay that log backwards, so you just undo what you did. Because cancel is the rarest thing, you see, so it doesn't need to be fast. I assume it's the rarest thing. Anyway. And whereas the commit is you just chuck it out, and then you get onto your next sub-transaction. And it worked, but it's a huge change in all the indexing code, and it's hard to construct it as a series of commits that anyone could review, and I've decided it's probably not worth even trying. So it doesn't help with search speed, which is really what we want. I had some ideas around that too, but I can't remember what they all were. There's branches on GitLab where they did pass all the tests, but that's all really. And one thing I came to think is that maybe we should actually, because with GUID indexes and operations in the index are relatively fast compared to how they were before, we might be able to just do more work in the indexing layer and reduce that subset down tighter around the real values, and it might be worthwhile. So I haven't tried it properly, but maybe I will. And if I don't even remember what that slide was about. All right, that'll do.